Welcome to Module 5. The topic this week will be assessing measurement quality. How do you know that the data you collected, read, or heard about are legitimate? These issues discussed in this module pertain to how you can better trust data to which you have access. Note that you should always be questioning and improving your own data with clients and participants, but even published data sometimes have these problems. Science is all about replication and extension to help provide evidence, not blind belief or reliance on authority. The desire to always want to verify whether something is true is a part of skepticism or philosophic doubt. Philosophic doubt is one of our guiding attitudes of science. We can never know for sure that what we observe and record is precisely accurate, but we can work to make our measurement procedures more reliable and increase the believability of our data. Accuracy is the extent to which observed values resemble the events that actually occurred. Reliability is the stability of the relationship between observed values and the events that actually occurred. If our data collection is inaccurate, is it at least inaccurate in a consistent way? For example, if we're collecting data on a client cursing, do we consistently miss instances of the behavior only when the client is whispering, or were we in some way inattentive such that many different instances were missed? Note that some sources talk about reliability in the sense of reliability across observers. In the assigned reading, Hartman provides a definition of this: the degree to which data can be generalized from a given set of ratings to those that other raters might make. We'll talk more about this in the context of inter-observer agreement coming up. Finally, believability is the extent to which the investigator can, in the absence of direct evidence, convince others to believe that the data are good enough for interpretation. During this module, we'll discuss strategies by which to enhance data collection along the dimensions of accuracy, reliability, and believability. First, though, let's review one more term: validity. Validity is the extent to which observed values represent the events that they're supposed to represent. In behavior analysis, our records of dependent variables are usually of high validity, so long as we complete direct assessment rather than relying on indirect measures. If our intention is to improve a client's fluency with single-digit math facts, for example, we would measure precisely that: their speed and accuracy of answering math problems. Their verbal report of their school performance or their satisfaction with the intervention would both be much less valid measures. Keep in mind, though, that even direct measures can be more or less valid, depending on the goal of your intervention. Assessment of math problem fluency in a laboratory setting is a direct measure, but if the goal is for your learner to improve performance in the classroom, your data may or may not correlate with that. Cooper, Heron, and Heward provide 3 criteria by which you can ensure that behavior analytic measurement is valid: use of direct measurement, measurement of a dimension of behavior relevant to the experimental question or intervention goal, and representative samples of the behavior collected when its occurrence is most relevant. If you determine that your measures are of a behavior that may not be precisely what you would like to change with your intervention, a good way to assess validity would be to at least occasionally measure that actual behavior of interest and determine whether your data correlate with changes in that behavior of interest. For example, if you're primarily able to collect data in a lab, you should at least sometimes assess the learner's behavior in the classroom. And for that matter, you could also periodically assess the learner's verbal report of their performance and see if that is correlated as well. Consider the validity of data collection methods in this case. Staff are supposed to keep a residential site clean by doing dishes, vacuuming carpets, dusting furniture, picking up things strewn around, cleaning bathrooms, etc. Consider what some valid direct measures might be. Direct, valid measures might include someone observing the cleaning behavior and recording it. A ceiling camera could also record the cleaning behavior. Less valid indirect measures could include staff rating their performance on a questionnaire. Verbal report about behavior does not always correlate with the behavior itself. Staff members could also rate the performance of other staff, and this is subject to some of the same problems. Administrators could rate the permanent product of how clean the site seems to be during an inspection, but this will not reveal how much cleaning behavior each staff member engaged in. Similarly, Someone could record the level of cleanser in the bottles on site, but whether or not those cleansers were used effectively will in part determine how clean everything got. As noted previously, it's not possible to 100% guarantee the accuracy of data simply due to the attitude of philosophic doubt. Repeated, reliable measures of the same behavior increase our confidence in its accuracy, however. If possible, it's also desirable to compare observed values to true values as evidence for accuracy. Some options for doing this include calibrating automatic measurement systems, collecting data from video recordings, and assessing behavior based on permanent products. In the first example, you could, for instance, compare data collected by a pedometer to the actual number of miles walked around a standardized track. If you're using a computer program to record responses, you could occasionally directly observe responding and perhaps video record it to compare your own measurement to that of the computer's. Most data are collected per session or observation. In these cases, even if you have evidence that the total count of the occurrence of a behavior during an observation is accurate, this is still not evidence that each tally of that behavior was accurately recorded when each instance of the behavior occurred. In order to gather better evidence of this, you would need to collect data during intervals of the observation and compare tallies of the behavior during each interval to the true values. The shorter the intervals, the more precision you'll be able to get. Are these data accurate? If 20 responses were made in a 5-minute sample of behavior and 20 responses were counted, those data are accurate. If 18 or 25 responses were recorded, those data are inaccurate. What if 20 responses were counted, but one tally was a response that wasn't made, and one response was actually made that wasn't counted? Those data are not exactly accurate, even though the total count matches up. If data collection lasted longer than 5 minutes, those errors would probably be more noticeable in the total count. Reliability of data collection across observers means that multiple observers collect data in the same way. This suggests, at least, that training of those observers was consistent in quality. If the data are also accurate, you're in good shape. If you have evidence that data are inaccurate but reliable, that can tell you how to proceed with additional training, or perhaps an update to the operational definition of the target behavior. You could also assess each individual observer's reliability of data collection by presenting them with exactly the same sequence of behavior and asking them to record data collection multiple times. Again, video recording would be a great tool for this. If the data collected are reliable, even if they're not accurate, you would then know more about how to proceed with training. In this example provided by Cooper, Heron, and Heward's text, 3 friends consistently ride the same bike path and check the length afterward. Bill reports how long he felt the ride was, rather than consulting a pedometer. Which of these measures appears to be reliable? Which are valid? Can you ensure the accuracy of any of them? We can definitely say that John's measurements are reliable, consistently recording 68 miles on each trip down the path. Both John's and Tim's measures are valid as they're directly measuring distance. If you recall from the reading, Bill's measures are based on how long he feels he rode. That's not a valid indicator of distance. We can't ensure the accuracy of any of these measures unless we had another means of measuring the true value. Here's another example of how we can consider whether data are accurate, reliable, or valid. Are these data accurate? Why or why not? What about reliable? Again, why or why not? Are these data valid? Why or why not? None of these measures accurately represent the person's weight of 160 pounds. The data are also not reliable. We're getting different errors each time. The data are, however, valid. A scale is a direct, appropriate way to measure weight. Now the scale's measurement results in a display of 160 pounds each time. Are the data accurate? Are they reliable? And are the data valid? Yes, all three qualities are met in this case. Here's one more case. Now the scale outputs a result of 100 pounds each time. Are the data accurate? No, the person's weight of 160 pounds is not represented. Are the data reliable? Yes, the error is by the same margin during each measurement. Are the data valid? Yes, the data are also still valid in that a scale is an appropriate way to measure weight. This chart from Cooper, Heron, and Heward is a great resource to reference when considering the utility of data that may be lacking accuracy, reliability, and/or validity. If data are valid, accurate, and reliable, the data are actually going to be useful for advancing our behavior analytic knowledge and creating or modifying interventions. If the data are accurate and reliable but not valid, how would you judge them? Those data would be meaningless since they weren't actually related to the behavior of interest. And if the data are valid and reliable but not accurate, they're always wrong since they were consistently inaccurate. Finally, if data are valid and accurate but not reliable, they're sometimes wrong since they were inconsistently accurate. Now we come to believability. Assessment of Inter-Observer Agreement, or IOA, is a procedure for enhancing the believability of data that involves comparing simultaneous but independent observations from two or more observers. Collecting IOA as support for believability of data is an established practice in our field. Published studies are generally required to have collected IOA for at least 33% of recorded data, and average IOA should be 80% at the bare minimum. Note that IOA does not inherently provide evidence for accuracy or reliability. Each independent observer could be inaccurate or inconsistent in similar ways. Cooper, Heron, and Heward note that IOA can help to detect observer drift over time, but it's important to keep in mind that multiple observers may drift in the same way, especially if they regularly speak to each other about the behavior and the client or participant in general. Here are the steps to approaching IOA data collection. Procedures for training observers and collecting IOA are typically reported in experimental manuscripts. Training generally involves the primary and secondary observers independently collecting data from the same video recording or permanent products, then comparing records. Disagreements are discussed, and this process repeats until 100% agreement is reached. A key facet of IOA data collection is that the observers must be independent. If observers are able to consult with each other during data collection or see each other's data, they will unduly influence each other. Next, we'll discuss how exactly to calculate IOA using different formulas, depending on the type of data you collect. The first equation is the least conservative. Total agreement is calculated by dividing the smaller total recorded by the larger total and multiplying by 100. It's typically used when observations are not divided up into intervals, but you really ought to do that and use a different IOA equation in order to support your data's believability. Next, exact or interval agreement. You calculate this by dividing the total intervals with agreement by the total number of intervals. This is also called exact count per interval IOA, and interval agreement is sometimes called trial by trial IOA. The only difference between exact and interval agreement is that in the case of exact agreement, continuous data are being collected during each interval, and in interval agreement, time sampling is being conducted. In the case of continuous data, if count within an interval is disagreed upon, even by one instance, it would decrease IOA. Mean count per interval IOA is calculated by determining the first interval's IOA by dividing the smaller record by the larger, then the second interval's IOA, thirds, etc., then adding up all of those ratios and dividing by the total number of intervals. This is a reasonable alternative portrayal of agreement, especially in the case of high-rate behaviors. In this case, if count was disagreed upon in an interval by one instance of behavior, that might lead to IOA within that interval of 90% if one observer recorded 9 and the other recorded 10. that percentage would then be averaged with the IOA of the remaining intervals, possibly leading to a final IOA that is still quite high. The most demanding method is occurrence and non-occurrence agreement. The equation is the same as that of exact or interval agreement, but you would report IOA for intervals in which the behavior did occur separately from IOA for intervals in which the behavior did not occur. When reporting IOA for interval data, if you do not report these data, be prepared to defend your reasoning why. For example, if agreement is 100% across the board, it would not be necessary to report the two scores separately. If you would like to review further discussion on this topic, Hopkins and Herman in a 1977 issue of the Journal of Applied Behavior Analysis discussed the importance of separating out these calculations of agreement.
Take some time now to practice with these equations. First, calculate the total count IOA, dividing the observation with the smaller count by the observation with the larger count. Both observers recorded 15 instances of the behavior, so total count IOA is 100%. How about exact count per interval IOA? Divide the number of intervals with agreement by the total number of intervals. There are 6 intervals and the 2 observers agreed during 2 of them, so exact count per interval IOA is 33%. Now, mean count per interval. The IOA per interval is noted in the right-hand column, so you will just need to add those up and then divide by the number of intervals. The mean count per interval IOA is 65.3%. Finally, occurrence versus non-occurrence agreement. Occurrence IOA, also known as scored interval IOA, is based on intervals in which either observer recorded the occurrence of the behavior. Divide the number of intervals in which the 2 observers agreed on the count of the behavior by the total number of intervals in which either observer recorded the behavior. IOA for intervals in which at least one observer reported occurrence is again 33%, 2 intervals with agreement out of 6 total intervals. How about non-occurrence? Divide the number of intervals in which the 2 observers agreed that the behavior did not occur by the total number of intervals in which either observer said that the behavior did not occur. IOA for intervals with no occurrence is 0%. No instances of agreement in the one interval that did have a report of no instances of the behavior.
Let's practice calculating IOA for a set of time sampling data. There are 10 intervals recorded here. Each row represents data collected by a different observer. That is, the white row of data was collected by one observer, and the gray row of data was collected by a second observer. X's mean that the observer marked that the behavior did occur during that interval. So, what is the interval by interval IOA? There are 7 intervals with agreement, so IOA is 70%. How about occurrence versus non-occurrence agreement, where you report the IOA for intervals in which observers agreed that the behavior happened separately from the intervals in which at least one observer recorded that the behavior did not happen? IOA for intervals during which at least one observer reported occurrence of the behavior was about 57%, 4 intervals with agreement out of 7 total intervals. IOA for intervals during which at least one observer reported no occurrence of the behavior was 50%, 3 intervals with agreement out of 6 total intervals. Once your observers are trained and you know how you intend to collect IOA data, you must also decide upon when and how often those assessments should occur. The answers to these questions come down to as often and with as great variability as possible. Again, IOA must be assessed for at least 33% of your total data collection. But that assessment must take place across participants in your study and across phases. For example, some IOA should be collected during baseline prior to intervention, some after your intervention has been implemented, and some during maintenance or generalization procedures. In a research manuscript, you would explicitly state that IOA was assessed for a certain percentage of your data collected across participants, phases, etc. In a manuscript, you'll always see the primary observer's data presented for analysis. IOA scores then allow interpretation of how believable that observer's data were. Scores are typically stated as an average across assessments, along with a range of scores. Readers ought to have some concern about low average IOA, even more so if scores were consistently low rather than just including an outlier or two. Low scores might indicate that observers were not trained very well regarding how to collect data, or that the operational definition of the dependent variables was insufficiently objective. Perhaps data were being collected on too many behaviors at once, leading to increased unreliability and inconsistency across and within observers. All you can know for sure is that the reported data are less believably representative of what truly happened. In summary, 80% agreement simply means that one observer's total count for a session was 20% higher or lower than the total observed by another. Although the investigator would know which observer had the high and low value, there would be no evidence about whether either count was accurate. On the other side of the coin, if IOA scores are consistently high, we must continue to bear in mind that this is not directly indicative of accuracy. However, it's safer to say that procedurally, observers were at the very least trained consistently and agreed upon a common definition of the target behaviors. IOA data should not be assessed at the end of a study or intervention, but rather consistently throughout the procedures. If a low IOA score is obtained, observers can then consult with each other to discuss disagreements. If there's any concern about the number of different behaviors or participants being observed at once, this could be addressed by providing further training to the observers to ensure that they're fluent in the data collection procedures, or simply by adding more observers so that each pair of observers could collect data on only one or two behaviors at a time. If definitions of behavior are vague or overlapping, those could be refined and clarified. Observers might also start collecting data with more refined tools, such as improved data sheets or gadgets. Note that these changes would need to be reported in a research manuscript. It may ultimately be the case that only data collected later in the study are worth interpretation if IOA improves significantly. The final tactic listed here is more complex than it might initially appear. Observation of supervisees will be a significant part of your job as a BCBA, and the same principles apply when training and checking in on anyone assisting with data collection and research. If you conduct these observations on a regular basis, reactivity will naturally decrease over time. Nonetheless, it's a good idea to observe as unobtrusively as possible and to ensure that you're not influencing the data collected by rewarding reports of some values over others. You can also periodically implement booster training sessions or rotate through different observers. Blind data collection in which the observers don't know the goal of the study can help with that issue as well. There are some logical issues with IOA. What if both observers agree, but both are equally inaccurate or invalid? What if one observer says a behavior occurred and the other one didn't? Who is right? Who is wrong? Ask yourself why enhancing believability in this way is desirable in our field. Adding a second observer will never tell you whether the first observer's observation was correct or not. This doesn't even get into discussion of collection of IOA for behaviors that occur in private or those that occur covertly. This is an ongoing discussion in behavior analysis, and no universally accepted solution has arisen. So far, you've practiced defining behaviors, selecting measures of those behaviors, and collecting data through a variety of methods. Our next activities will be focused on assessing and improving inter-observer agreement. You could simply collect IOA data and deal with low scores if they happen, but it's far more advisable to plan ahead and determine how you can help ensure good agreement in advance. When you do have your data, what equation will you use to calculate IOA? In addition, how will you promote accuracy and validity of your dependent variables, given what was reviewed in this module? Given your experimental question or intervention goal, be sure to select dependent variables, measures, and data collection methods that have a higher chance of allowing accuracy and that reflect what you intend to measure with good validity.